I'm extremely grateful to present my work, Continual Learning with Dependency Preserving Hypernetworks. Myself, DUPATI SRIKAR CHANDRA, and it's a joint work with Dr. Sakshi, Varshney, Dr. Srijith PK, and Dr. Sunil Gupta. Humans learn continually throughout the lifespan without the forgetting and often transfer the knowledge from one task to other task. But neural network suffers from catastrophic forgetting. While learning new tasks, it forgets the knowledge of the previous one. Here we can see a plot of split-MNIST tasks that learning sequentially. While learning new tasks, there is a significant drop in accuracy of the previous one. Hypernetworks are secondary neural networks that generate task-specific weights of target network by taking task-specific embedding ET and chunk embedding C as input. Chunked hypernetwork generate target network weights in smaller chunks for model compression, but chunked hypernetworks assume independence across the chunks. Here we can see each chunk generated independently from the other. So we aim to propose an LSTM based hypernetwork which can maintain dependencies across the chunk while also maintaining parameter efficiency. And we also propose a novel regularization for hypernetwork based continual learning and a network growth technique that doesn't require regularization. So in this we can see LSTM based hypernetwork architecture. So LSTM based hypernetwork takes task specific embedding ET and chunk embedding as an input to generate the chunk. While generating the next chunk, it uses the hidden state and self state of the previous chunk to maintain dependencies across the chunk. All the generated chunks combine together to get target network parameters, and that are used by the target network to map from input to the output. In continual learning scenario, we use regularization based approaches to mitigate forgetting, but regularizing all the parameters is not a good idea because not all parameters contribute equally for a specific task. So we aim to assign important scores to the each weight and updates are done accordingly. And important weights of a specific task are constrained while other are freely lent for the new task. Important scores for the weights are computed using Fisher information matrix, noting that the Fisher information is computed over the main network parameters but not on the hypernetwork parameter. One potential problem with this regularization based approaches is training time grows with the number of tasks. So we aim to propose a network growth technique specific to LSTM with the intuition that the actual main network parameter differ across the task, but the dependencies between them remains the same. So the hidden weights of LSTM are shared across the task, but the variability in parameter generation across the task is captured by having task specific weights associated with the inputs. The weights associated with the inputs are task specific. Conducted our experiments in both non-replay and replay-based setup. Our proposed approaches LSTM net with IWR regularization, LSTM net grow, which is a dynamic architecture-based model, outperformed or maintained results compared to the all existing baselines in all three continual learning settings on split MNIST and permuted MNIST. Similarly, even in replay-based setup, our proposed approaches outperformed all the existing baselines with a significant margin. We conducted experiments on complex dataset splits of CIFAR10 and CIFAR100 with deeper models. Our proposed approaches outperformed existing baselines with a significant margin even on a complex dataset. Finally, to summarize our work, we proposed an LSTM-based hypernetwork for continual learning to maintain dependencies by also maintaining parameter efficiency. Our proposed IWR regularization is well suited for all hypernetwork-based continual learning approaches, and our network growth approach outperformed all the baselines.